Hello, hi everybody. Today we are going to discuss about question 13.2, condensed matter physics. Show that near the top of the energy band, the density of state is given as in equation 13.30. This one. So we need to show this. Okay. All right. Disclaimer first of all. This is only my thoughts, okay, and also my hypothesis based on my understanding. All right, so which means I'm open to any critics and also discussion with you guys. In case you are, well, do not agree with my solution or whatever my calculation, so you can argue that. Okay, so as you can see over here, the equation we need to prove is actually similar to what we have dealing previously, which is the 3D bulk density of state, right? This one. So we already familiar with this. We know how to derive it. Of course, we need to have to use a spherical coordinate. Okay, you need to know the concept of the x space or the position space or real space, and also the momentum space or basically the k space or the reciprocal space, as people usually say in solid state physics, right? Okay, so for x space you have the volume as the L cube, okay, referring to the cubical three-dimensional shape, right? For the k space or the momentum space, the volume Vk is actually a pi cube divided by V. So V is from the x space volume, alright? Okay, so we need to have the expression for Vk in terms of K, because from this we can derive the density of state. Alright, so we need to use the spherical coordinate. So of course we already familiar with this. So this is the volume element of the sphere, okay? But this is in x space. We want to have in k space. So dvk is just change everything into k. Okay, k square sine the angle is maintained. The theta and the r becomes dk. So this in k space, momentum space. All right, it's pretty simple. Then we need to integrate twice with respect to angle theta, phi and theta. Okay, so phi is the azimuthal angle and theta is basically this one. Okay, all right, and we integrate only twice because we don't have to integrate the with respect to k, because of course the k depends on the energy. So later we will substitute, okay, k as in terms of energy, so that we can get the density of state in terms of energy. All right, so we don't have to integrate that. And at the end you arrive to this expression. Okay, dn equals to vk square over 2 pi square dk. Okay, so next page is quite puzzling or controversial, I could say. All right, so this is actually the way I just define, okay, et. So et is technically the energy on the top of the band, near the top of the energy band, sorry. Okay, so I define et in such a way: ECB minus EVB. So ECB is basically, okay, so let me just show you what is ECB is basically. Oops. Okay, so the energy over here, of course the electron excited, so left behind on the hole over there in the valence band. So this is valence band, this is conduction band. Okay, so get excited. So E conduction band, ECB, okay, equals to, okay, C small b equals to, so EC over here, the minimum. So this is the minimum energy for the conduction band, and then this is maximum energy for valence band. All right, so you need to know that. So ECB equals to EC plus the energy of the electron h bar square k square over 2m e. So this is effective mass. I just write it. Usually people write it as n star, doesn't matter. So for hole, perhaps this should be E, valence band. So of course from EV, so the energy decrease, right? Because this is a more negative side. So it should be EV minus h bar square k square over 2m whole, effective mass for the whole. Okay. Alright, so how I define the ET is like this. Okay, so from here to from here to here, so I define this to be ET. Okay, so near the top of the band is basically this energy difference. All right, so ET. So basically if you want to get this, you need to subtract ECB minus EVB. Basically you just add up, right? Because this is positive side and this is negative side. So positive minus negative side, so it becomes positive. Technically you just add up. All right, so okay, ET as I define, ECB minus EVB equals to EC plus H over 2 ME bracket E, so valence band, sorry, EV, should be EV, right, minus H bar K square over 2M whole. So you will see straight away, so this is EC minus EV, right? So EC minus EV, what is that? Pretty easy, that's the energy gap, the EG, right, which is this one. So I can define EG to be just E, no worries. Okay, plus, so I just factorize H bars K square over 2 1 over ME plus 1 over M whole. So this you can just define this to be 1 over M, the reduced mass of them. So this should be M whole plus M electron M whole. So this is 1 over M. I mean approximately, not exactly. Okay, 1 over M. So that's why I get this expression over here. Alright, so I hope that's very clear, right? So I just let EG, the band gap energy, to be E. Okay, so it doesn't matter. So that's just a matter of defining the variable. Okay, and then I just take the derivative with respect to E. Okay, I just get this. So of course you already know this. Okay, so derivative with respect to E on the left side, and then on the right side with respect to K. So basically this is actually dE over dK. Okay, so I make dK as the subject of formula, so it becomes like this. So actually this is K, right? So I substitute, because actually from here, so this is the previous expression we get. Basically we want to eliminate this K square and dK. So we don't want to have any K, we want to replace K to energy term. Okay, so this I just replace K square to be what? Yo, I forgot. 2M E T minus T, T minus ET minus E over H bar, right? H bar square. Yep. Okay, so that's K square. Then dK square, 2M ET, am I correct? No, MDE, sorry, MDE. So MDE over H bar square root 2 ET minus EM over H bar. Alright, so just replace these two guys. Okay, I'm checking if my expression is correct. Yeah, Okay, so this and this cancel. So you just well, just simplify the term. So at the end you'll get this. Oh yeah, don't forget to multiply by 2. In this step you need to multiply by 2. Why? Because the case that it can have 2 electron with different spin, of course, because we don't want to violate the Pauli exclusion principle, right? So 2 electrons for one case state, but different spin, up and down. So cannot up and down cannot. So that's violate the principle of exclusion principle, right? So this is known as the 2 spin degeneracy. Okay, you know degeneracy. I mean, degeneracy is when for example electron have same energy level. Okay, they have the same energy, so we call it degenerate energy level. Okay, so yeah, at the end just multiply by 2, you got this. So actually, because after I multiply by 2, I want to differentiate between the n and the n times 2, which is this one. So this is actually the n times 2. Well, of course, you can replace back the n to be the m prime to be the n, so like that, so that nobody confused. All right, and at the end of the day, you are able to show the expression. Yeah. Okay, so for question 13.3, okay, so I want to discuss about these two. Okay, so h bar omega is basically h bar 2 pi f. Well, nu, you can use nu or f, and nu is frequency. So frequency is basically, okay, let me check the dimension. So s, so this is v, velocity of the wave, lambda. Okay, so v like this. So 2 pi over lambda is the k vector v. So because we are dealing with phonon, so well, velocity of sound in solid, because we are dealing with what, with silicon. So silicon is solid. All right, so we need to check what is the velocity of sound in solid. So the k vector is basically, okay, because we are dealing in the Brillouin zone. Okay, so if you still remember, so we have, what is this? So this is lattice. Okay, and each atom is arranged in a lattice. So Brillouin, how to spell, I have to pronounce that, Brillouin zone. Okay, in Brillouin zone, blah 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 blah. Okay, Brillouin zone. So Brillouin zone is basically the primitive lattice space, right? If I'm not mistaken. So how to do this is basically, okay, I want to have this, so it needs to perpendicular, right? Perpendicular, and then with this perpendicular, and then with what again? So with this perhaps, so perpendicular, and with what else? So with this perhaps, so it needs to perpendicular. Okay, I mean not only perpendicular, perpendicular, and this having same length, right? So perpendicular bisector, yeah, bisector, right? So I just remember that terms. So this is Brillouin zone, so the primitive lattice, primitive zone, is it? So if I remember it correctly, sorry for that if because I already forgot. Okay, so the Brillouin zone, where's the Brillouin zone? This, so the intersection, this, so this is the Brillouin zone lah. Okay, so the near the edge of the Brillouin zone, like dekat tepi lah kan, the edge of the Brillouin zone, so we have k equals to max, maximum maximum. So if it is not the edge, like macam dekat sini, for example there, okay, or anywhere beside near the edge, then the lattice the wave vector is not maximum. So but but the condition is near the edge of the Brillouin zone, so the wave vector is maximum. So remember, the wave vector is given by what? N pi over lattice constant. So this is lattice constant A. So lattice constant for silicon, you may search for it lah. Okay. So I choose n equals to 1, so pi over A, no problem. Okay, so back to our question. So h bar k, so k is berapa tadi? Pi over A. V sound. So you can search for this and then you will get the answer. Okay, and for momentum is very simple. So h bar k. Okay, and for question B is basically to verify if the silicon has the indirect band gap transition. So this is actually my draft. Okay, so I'm not sure if this is correct, but this is only my thoughts. Okay, so this is the first step, right? So first step, we need to because we want to excite this for electron. Sorry, we need to supply enough energy. Okay, of course, this electron cannot directly jump there, so it needs to transition temporarily somewhere. For example, here, and then for example here, and then there, or in this case here to there, right? So that's just my thought. Okay, so yeah, I want to provide a scheme to check if the silicon really has indirect band gap. So I just wrote something random like this. Yeah, perhaps tomorrow I'm going to check this. Okay, so yeah, that's the only thing that we have to discuss today. So yeah, 13.2, that's only my understanding, based on my understanding and my thoughts, and 13.3 is also based on my solid state physics knowledge, right? So hopefully everything goes fine. Thank you so much and good night.